My name is Phil Gough, and I'm here from the University of Sydney with my co-authors Praneeth Perera, Michael Kertesz and Anusha Withana to present a paper titled Design, Mould, Grow, a fabrication pipeline for growing 3D designs using myco-materials. Myco-materials are being used in fashion, architecture and product design. The literature shows that sustainability is an important consideration in HCI, with methods, workshops and example designs demonstrating its impact. Sustainability is also used as a critical lens to view HCI projects and to demonstrate how sustainability can be achieved through design. We also see new methods and approaches emerging, such as life-centered design, more than human-centered design, and non-human personas. While we will be talking about designing with mushroom-based myco-materials, designing with living materials also includes approaches such as biodesign, bio-HCI, and biodigital hybrid systems, in particular using synthetic biology to grow living systems as part of interactive systems. We see examples of myco-materials in interaction design, fashion, architecture, prototyping, and other fields, but in an HCI context, we often see myco-materials being used as a structural housing, particularly for electronic systems, or by peeling back the skin or leather from the mycelia in order to make wearables. So what actually is a myco-material? The root network of a mushroom fungi is called a mycelia, and in some species, this binds together a substrate as it grows. This bioaffordance of mycelia, the way it creates lightweight, rigid structures, provided us with an opportunity and the motivation to think differently about the design of interactive things. With this growing urgency for utilising alternative materials in a design context, whether for prototypes, design products, we wanted to understand what the process is to grow and design with myco-materials, and also understand what some of the limitations of the material are and what 3D forms we can encourage the living material to take on. We used a material-driven design process to understand the material, create visions for what it may be used for, as well as creating a software intervention that we hope may be helpful for HCI researchers and designers. So let's start with the process. The four things that come together to grow myco-materials are the fungi species. In literature, we often see oyster, turkeytail, and reishi being used. It requires a substrate for the fungus to grow on, often a wood-based material or a waste such as sawdust or paper-based waste. It requires a supplement similar to a fertilizer and usually provides nitrogen, and as our examples will show, we can also have inclusions. These are additional materials that can be consumed by the fungi but are not the essential food that it needs. Examples are paper-based waste or spent coffee grounds. The process to make your own myco-materials, generally the first step is bulk growth, allowing the fungi to take over the substrate. After this stage, the fungus has taken over its little ecosystem and the myco-material can be broken down and placed into a sterilised mould and allowed to grow for a few days. Once sufficiently colonised, the myco-material can be demoulded and allowed to grow on the newly exposed face. So that way you have more complete growth over the entire body of your design. After this open growth stage, which may take a few days, the myco-material is dried at a very low oven. We typically use between 30 to 80 degrees Celsius, and domestic ovens aren't very accurate at those low temperatures anyway. During use, the fungi will be dormant, but can potentially be reactivated with moisture or simply composted at the end of use. We can see that there is some alignment between this slow process of growing and a design cycle. 3D model design could take between minutes and hours depending on your expertise, and this needs to be converted into a mould. And also embedded hardware may need to be programmed. Now this could be done during the bulk growth phase, and then the bulk grown mushrooms can be broken down and added to the mould at the same time as your embedded hardware, and then the process continues. After use, the myco-materials can simply be broken down by hand and the electronic components removed, and then the myco-materials themselves can be composted. Our initial exploration included 2 trials in order to establish an appropriate species for us to use in our context, as well as an appropriate substrate. We identified 2 challenges to overcome if we were to move to our HCI lab. The first was infection control and controlling growth conditions. To address this, we changed from growing on our own sawdust to using grow-it-yourself mushroom kits. The second challenge was related to mould design and how we could design for easy removal, and our solution was to produce a grasshopper plugin for Rhino 3D. We can see from the examples here that the growth process was much quicker as the bulk growth stage had already been done. And second, we were able to generate complex 3D molds from standard 3D objects. And this allowed us to ask the question, what actually can we grow? What are the limits of the 3D forms? What's the limits of molded designs? And what are the mechanical properties of the myco-material? So to explore this, we produced a series of trays to examine the surface qualities that we could produce from myco-materials and how well they rendered them. These were grown with no inclusions and with a coffee inclusion of 30% spent coffee grounds, and also the circular trays seen in subfigure C here included a glycerin treatment. This is used to soften the material, a bit like a moisturizer. Several of these were then 3D scanned or tested mechanically. Using the grow-it-yourself mushroom kits also allowed us to undertake this in an apartment during COVID lockdowns, so it's eliminated the risk from infection by having a very healthy mycelium from the start of our design process. So to summarise the outcome of our geometric analysis, our mix shrank to 92% of the original dimensions after drying. On the circular tray shown on the left of this slide, the coffee included object, which is the one we can see, showed the lowest mean average error from the ideal at 1.78 millimeters. The plain inclusion-free model was next at 2.16 millimeters, and then the glycerin treated after that. The chart on the right shows that the larger convex features, the protrusions out from the surface, had the lowest mean average error, followed by the largest convex curves. So we found that large protrusions and patterns work relatively well, but anything less than 5 millimeters becomes unreliable, but textures still can be used. We had 4 samples with each condition tested 5 times to measure force at a fixed displacement, and the material performs as an elastic material, having less force required under relaxation compared to compression. Adding coffee increased the slope or the modulus of elasticity, but treating with glycerin impacted the mixture with coffee, but not the mixture without coffee. As the myco-materials are often used as insulators, we also measured the insulation properties of myco-materials. With an understanding of the properties of the materials, we were able to develop some concepts of how they might be used. To utilise compression, we grew a coffee cup coaster that has a force-sensitive resistor inside, which could potentially be used to track water consumption throughout the day. To make use of its insulation properties, we designed a cup holder. As we were able to treat the surface of the material, we included an icon that changes colour as the coffee cools down. For its ability to generate textures and to be composted, we created a concept for a pot plant which could be consumed as the plant itself grows. We also included a concept for myco-material housing. This houses a soil moisture sensor with embedded LEDs that glow red when the plant needs to be watered. By growing myco-materials, we also identified challenges for researchers and practitioners who don't have experience with mould design. These included understanding draft angles, interlocking pieces, and designing the negative forms required to make the positive object. So we present Design Mould Grow, a piece of software built in Grasshopper for Rhino 3D. This allows us to select an object inside Rhino, scale it to compensate for material shrinkage during drying, smooth the surface to remove small features that won't render properly. The application allows us to create and move various cutting planes up to 5, and then create and move an air inlet that is necessary while the design grows. It also allows us to review the draft angles, and this allows us to identify where the part may catch the mould when it is being removed. In this example, we can see that the ears of the bunny are probably going to be impossible to remove from the mould, and so more cutting planes may be required. The software is able to reduce the amount of 3D printed material by having a rough shape rather than a bounding box. The bounding box is useful for small objects. We have also included a lip with holes so that the mould can be tied or pinned together. As myco-materials are becoming more common, there is a need for HCI to understand its impact on the prototyping process, the user experience with prototypes and how that is affected by sustainable materials, and ways that we can identify and reduce our waste in the prototyping process. In the future, we also hope to explore 3D printing and the opportunity to create complex forms from myco-materials without the need for 3D printing plastic molds. We hope that Design Mould Grow will be a useful software tool for people who have less experience with mould design but still want to be able to utilize myco-materials in the design and prototyping process in the HCI Lab.